A warm welcome to all of you to Support Vectors sessions. Our topic today is dimensionality reduction. So we will launch into that. Yesterday, we did clustering. I hope all of you who were interested in getting the source code did go to the course portal and get the source code. Remember, it's absolutely free registering for this portal and getting the source code. Please do that if you're interested, or reach out to somebody on Discord and they'll help you do that. With that out of the way, let's get started now. Okay, this is a bit cumbersome. Okay. So the topic today is dimensionality reduction. And we'll talk about quite a few methods to deal with that. Just to recap, we have already finished quite a few topics. We have finished regression. We have finished classification. We have finished clustering. And we have done statistics very briefly and data analysis, visualization. So today is the final section. Those of you who happen to come here for the first time, all of those sessions are recorded. They're already there on YouTube. They're already also there on the course portal. So please avail yourself of that. And so in this progression, the last topic is our dimensionality reduction. All right, so with that stage set, let's now continue. What is dimensionality reduction? In a very simple way, suppose you get data, lots of features in it. The X vector, suppose you have X1, X2, Xn. So we take all sorts of examples. Let's say that, let's go back to the example of diabetes. You want to predict whether somebody is predisposed to get diabetics or not. To determine that is, you need, as a physician would tell you, you need meaningful factors. The trouble with machine learning is sometimes you don't know how important a factor is. It may be very relevant or it may not be relevant at all. For example, age is a relevant factor for adult onset diabetes. Weight and BMI are relevant factors. Food, many such things, hereditary are relevant factors. But the color of your shoes that you wear regularly to work may not be a factor, right? Would likely not be a factor. Or how many penguins jumped off Antarctica into the sea in Antarctica from an iceberg would not be a factor. So it's very easy to think of things that would not be a factor, except that most of what we think irrelevant or what we think relevant deals with situations which we are very familiar with. Diabetes has been well studied for generations. On the other hand, when you get new data and you have to build a prediction model around the data or see patterns in the data, sometimes it's not so obvious which factors are important and which factors are not important. It is only a posteriori, after you do a lot of experiments and modeling, that it emerges that certain factors may not be important. Right? So finding out the unimportant factors and throwing them out is perhaps the most elementary form of dimensionality reduction. So for example, in this case, your data has n factors. So you can say that X vector belongs to an n-dimensional space, right? If you could somehow reduce this to, let's say, a smaller space, suppose you could say a new set of variables you could create out of this. Let me call it xi, belonging, well, there's a Greek symbol, why use that? Let me just use X prime. Belongs to a dimensional space D, where D is smaller than, significantly smaller than n, right? So what you're saying is, suppose I could throw some irrelevant factors out. That would be awesome, isn't it? There's not noise in the data. You're just throwing noise out. But even the discovery of the noise is quite often an insightful activity to know that this doesn't matter. Are we together? So for example, many people, when the COVID started, they began to believe that if you drank certain concoctions, it would cure you of your COVID. You don't have to take precautions, right? Or it would give you immunity to those to COVID, right? Nevertheless, how do you know what to do? One way is you can look at the trusted source of the information. Is it trusted or not? But when things like this happen, let's say when COVID happens, even the sources that you trust do make mistakes and they make statements that may not be true. And so it is only after scientific investigation or a data science exercise that you realize that some of the guesses, they look very plausible. They seemed as though they would matter, some factors, but in hindsight, they didn't matter at all, right? So that is dimensionality reduction. So it's the simplest form of dimensionality reduction. Let's just call it weed out irrelevant factors or features. This is about as lucky as you can be. If you can find features that don't matter at all, throw them out. You're done. But suppose you can't do that. Suppose some features matter, but they matter so little that to the first approximation, you can throw them out, right? So then what do you do at that moment? So then we come to a set of techniques that we'll talk about. And I'll motivate this with an example. Let us say that you have data, simple data. The data is like this. Would you agree that if I have axis x1 and x2, I can say that the coordinates of any point is given by the x1 and x2 coordinates, right? The vector, any data point is given by x1 and x2 coordinate, right? What in normal coordinate geometry you would call the xy locations, isn't it? Let's call this vector x. But observe something interesting. How much information would you lose if the only thing I was looking at is the location of x given by a function, let me call this x prime, which is just the distance from the origin along this line. A new axis that I created, a red axis, right? And I said that I can define this point as so far from the origin, right? Along this red axis. So you say, wait, that's not quite correct, because let's say that the point is here. You are missing out some information. The point isn't sitting on the line. It is lifted off the line a little bit. Do you see that, guys? Right? To the first, now you say, how much does it matter? Right? So one way to put it is, if you are going to take a flight to a city, broadly speaking, you want to know which city you want to go to rather than which specific neighborhood of the city your friend lives in. Right? It doesn't matter as far as flights are concerned, because there are only so many airports. Right? You just need to know which is the nearest airport you're going to. So based on real world needs and real world situations, there are times when when you do an alternate representation, let's say that x prime is equal to x1 prime, x2 prime, x1 prime, this distance being x1 prime, the x2 prime, this distance being, let me mark this distance, this being x2 prime, the lift off the axis, diagonal axis, the lift may not matter. Are we together? Right? Or another way to think of it is, imagine that this is a subway that goes only in a straight line, right? Then how far off the station you are, it doesn't matter. You just need to find the nearest station on the line. Does it make sense? right? That is it. So in other words, there are times where all you want to know is where are you in that one dimension, that line. The other, it doesn't matter so much. I mean, it does matter, but the first order effect is where am I on this line, right? And that is, so in other words, even though x1 prime vector is written as x1 prime and x2 prime, the x2 prime, the lift, does not matter, and I can represent the value just as x1 prime. Are we together? So that's one form of dimensionality reduction. Here what you're saying is, it isn't that x2 doesn't exist, x2 prime doesn't exist. It's just that if you judiciously choose an axis, a principal axis, then the off-principal deviations, maybe we can ignore it as a first-order approximation. And therefore, we can do a dimensionality reduction of the data. This argument is predicated on the fact that you can intelligently find the best principal axis, isn't it? The axis that data is most proximal to, closest to, hugging, which is that axis such that most of the data is very proximal to it, right?
But does the deviation amount matter?
Yes, the whole question is how much does the deviation matter? Hold that thought in your mind. Okay. But suppose you could say that there are situations in which these deviations don't matter. Like I said, when you're on the subway, that only goes in a straight line. The only question is, where do you get off?
These are only for some use cases.
For some use cases, yeah, for some use cases.
That was my question. Will that depend what axis to remove depend on the use case? The question you're trying to.
That is right. For the use case, it does depend on the use case. But it turns out that there is a vast number of use cases where these minor deviations or perturbations off the axis can be ignored. Are we together? So I'll give you an example. Suppose, let's take it, or let me take an example where it truly is. I will give you many examples. Like, for example, imagine that there is a bright source of heat, right? So right in the center of the room, there is a bright source of heat, and you're standing a certain distance apart. Your coordinates are XYZ coordinates, actually, right? Certain thing. But if you're better off right off the bat, you realize that instead of thinking XYZ, let's think spherical coordinates, how far you are and at what angle you are, and so forth. After a little while, you'll realize two things: that you may be somewhere far from the heat, and because hot air rises, right? If you go up along the inclined direction, the angle of incline, you move up a little bit, the temperature would rise, isn't it? Because hot air rises. Nevertheless, you realize that the primary, I mean, that will be a very small minor perturbation compared to the overriding factor that temperature is decided by how far you are from the fire, right? The source of heat. You have done that. If you have ever been at campsites, you must have realized that you tend to come closer to the campfire. You don't tend to stand up to get more heat, isn't it? Your first instinct is to come closer to the campfire. Why? Because from experience, you know instinctively that you're going to get far more heat by coming closer to the campfire than by rising up. Nevertheless, yes, given any distance from the campfire, perhaps if you moved up a little bit, almost an imperceptibly small amount more of temperature could be there, right? So that's a classic example of data existing in 3 dimensions, but the only dimension that matters is just the distance to the source of the heat. Do you see that? So that is again a situation of dimensionality reduction. Am I making sense? It turns out that these situations that I'm contriving on the spot are not as contrived or as rare as you would imagine. Our field is replete with data in which certain features matter more than others. In fact, quite often, the first 3-4 factors matter a lot. and then the other factors don't really matter. Are we together? They matter in smaller and smaller and smaller amounts. Some people call it the long tail effect. Quite often, it is common, not always true, not universally true, but it is quite common to see this in data. And therefore, the case for dimensionality reduction, isn't it? Therefore, the valuable technique of dimensionality reduction. So what I'm going to do is because this is an introductory class, I'm going to do something fun. I'm going to introduce a bit of mathematics. Usually you wouldn't, but I want to do that because it retraces the history of dimensionality reduction. The first technique that came out for dimensionality reduction was initially attributed to some folks in Europe. Then they discovered some other folks had discovered it. Then they discovered some other folks had discovered it even before. And it turns out that they had more or less independently discovered it in different fields. Okay? And when you look at the history very carefully, and at one time I went and looked at the history very carefully, it turned out that the first person who discovered dimensionality reduction, and in particular a technique that today we call, in new language, principal component analysis, right, was a mathematician named Kosambi. He happened to be from my university, my undergraduate university, IIT BHU. So, but when he discovered that India was still a colonial territory of the British Empire, so he sent his paper to be published. It actually surprisingly did get published, but it got completely ignored. Who's going to read the paper by some unknown colonial mathematician, right? So it stayed ignored, and he actually went on to do a lot of seminal work, some of which were recognized after the country became free. He and his father actually together, they were a pair. It's very hard to tell. Did the father do this or did the son do this? Because there's Father Kosambi and Son Kosambi, right? And one of them innovated the field of who really took numismatics, or the study of coins, as one of the foundational means to do a scientific study of history, or to establish what happened when and where by studying ancient coins. So I will retrace more or less the argument that Kosambi made for fun, but it's a little bit mathsy. But I think I'll try to make it so easy. Hopefully it won't feel mathsy to you. All right. So, and I'll also relate it to linear regression. How's that? So think about it this way. The way I'll motivate it is, imagine that, and I'll actually, there's something funny I'll do. I'll write PCA and somehow I'll relate it to something called correlation. And therefore, to linear, one-dimensional linear regression. Simple linear regression. It turns out that they are quite a bit related. So look at three situations. Suppose you have data like this. And now I won't use x1, x2. Forgive me, I'll just use x and y. Treat y as the response variable. Can you predict the value of y from x? I'm contextualizing the problem that way. Right? And deciding. So this is situation A, this is situation B. And let us make a third situation, much neater. A, B, C. Now, look at this. When X increases, there's a term in statistics called correlation. Correlation, or more strictly, correlation comes to normalized variables, but unnormalized, it is called covariance. The word is covariance. What is covariance? If one increases, does the other correspondingly increase? If one decreases, does the other correspondingly decrease? So first let's look at the C first. If you increase X, does the value of Y seem to increase? It certainly seems to increase, isn't it? So you would say that the covariance is positive. there is a distinct, clear covariance, pronounced covariance. And while we are at it, might as well throw in a different situation, D also. When we look at D, and once again ask this question, when X increases, does Y or decreases? When X changes, varies, does Y vary with it? Right? It does, right? But it varies the opposite way. If you increase X, Y decreases. In other words, it sort of contravaries, right? Or the way people typically or more formally say is negative covariance. They do together vary, but in opposite directions. So you say that here for D, covariance is negative, smaller than 0 for D, right? And for C, covariance is positive. It is really pronounced positive. They are very distinct cases. Now look at A. What would you say about A? If X increases, does Y increase or decrease? Not at all. You can't tell. For every point where you seem to have a bigger Y for a bigger X, there is another point which has a smaller X, smaller Y for a bigger X, isn't it? They're equal points in all the 4 quadrants, right? So here you would say that the covariance is equal to 0 approximately, right? You can't say. There's no distinct relationship. Are we together? Right? Now, this concept is called covariance. Now, what is called correlation is nothing but covariance of the normalized values. In other words, if I scale the value, z value it, x and y, correlation is nothing but covariance of this. So think about it. How did I do that? What we did is, do you notice that I put origin at the center of the data? Right? So I'm looking at every point xi, but because I put the center, first thing you need to do, so suppose data comes to you like this, and you have data like this. You need to go, so suppose this is x and this is y. What you need to do is first you need to go and sit squarely in the center of the data. You need to change your coordinate system. Then it is easier to see. Just how is it easy to see? Just check, do you have most of the points in the first and the third quadrant? Isn't it? It's positive correlation, covariance. If it is in the second and fourth quadrant, then it is negative covariance. If it is all over the place, no covariance. Easy, isn't it? So this new coordinate system, you can convince yourself, is nothing but xi minus mu for any point xi prime is this, right? And likewise, yi prime is yi minus mu x, mu y. Means the mean of, you're just shifting the coordinates to the center, isn't it? Does it make sense? And now, what is true about points in the positive quadrant? The product, if there is a point here, would you agree that xi prime times yi prime would be positive? Isn't it? And likewise, in the third quadrant, first and third quadrant, and because xi and y are both negative, it will still be positive. So now this is, by the way, people often ask, they have seen this equation for covariance. It looks rather scary, isn't it? How did people suddenly come up with this? It is actually as simple as that. You realize that when you multiply xi by yi, right, you realize that for positive covariance, this quantity is greater than 0. And for negative covariance, xi prime, yi prime would be negative. So what do you need to do? All you need to do is ask. There will still be some points off diagonal, right? For example, here there are some points that are still in the other quadrants, but majority are in the first or third quadrant, or are the majority in the second and fourth quadrant. One easy way to do that would be xi, yi, sum it up, isn't it? So sum it up. And if it so interests you, it doesn't matter, because all you're looking for is the sum, right? The signature, positive or negative. It will tell you that, isn't it? But if it really want to be more precise, you can divide it by the number of points. What are we looking at? This is literally the formula for covariance, effectively, right? And so this is how it is. And now, sometimes, data is elongated. You want to normalize it. For example, if you're looking at an elephant's height and weight, or right, height might be in meters and weight may be in pounds. One scale is too big, thousands of pounds. Another scale is 2 meters or something like that, or 4 feet or 10 feet. So you want to normalize the scales. So if you were to do what is called z-scoring of x, which is one step further, xi minus mu of x over standard deviation of x, and zy is xyi minus mu of x. But by the way, did I explain what mu is? Mu is the mean. Sorry, I must say mu is the symbol for mean, average of x, average of y, right? That's it. Are we together? And now, if in this formula you replaced, you didn't do this, you instead do zx, zy, everything remains the same. Remember, the quantity will still be positive only if you have positive covariance, right? This thing, when you deal with it, and again, do it with I, and do your usual game, sum over I, and this is called the correlation. That's what correlation is. Are we together? And correlation will take on values from -1 to 1. You can convince yourself. So that is the concept of correlation and covariance. So D, correlation will be negative. Covariance will be negative. A, covariance correlations will be approximately 0. What about B? Using our intuition, are there more points in the first and third quadrant, or in the second and first and third? So you would say that the covariance and correlation are positive or negative? Positive, but not as positive as C. C is in a very pronounced way positive, right? So that is, so in other words, you can have degrees of covariance and degrees of correlation. It's a measure. Do you see? So this is the idea. Never, at this moment, needless to say, one of the common fallacies of the human mind. So now that we know correlation and this, needless to say, it's practically a thing. I'm sure all of you must have been taught in school that correlation does not imply causation, right? Why is that so? Like, for example, isn't it obvious that if you increase x in the case C, y increases? So therefore, x must be causing the increase of y. Let's just do a quick refresher. Why is that not true? It is pretty obvious. Look at this. I increase x and y increases. So x causes y.
You could think the other way around too, right? Increase y, it increases x.
Yeah, sort of. If you just mirror the axis, in reverse the axis, it would look as though this is causing it. Go ahead.
Just another variable which is actually causing y.
A latent variable. Very good. Very good. That x and y may be caused by an underlying variable, right?
Which
so
is suppressed. Which is suppressed in this case.
Which is suppressed, which you don't see, which is not there in the data. Okay? So, for example, you suppose you couldn't see temperature, right? And you would just look at the number of children on the beach and the number of adults on the beach. Or both would, the more the children, the more the adults. The less the children, the less the adults. But underneath both, children are not causing adults to show up at the beach or the vice versa. But it's the temperature. A warm and pleasant days is causing families to go out to the beach. That's an underlying factor that's influencing them. So, right. So see, all you can say when there's a correlation is it's worth looking at it seriously. is there a causative factor? Is there? You don't deny that. You say, is there? What is going on? There may be latent factors, or it may be completely spurious. It may be completely accidental, right? And the internet is filled with hilarious, coincidental correlations. It's just amusing. There are entire books and things like that about very peculiar coincidences. Right? So, suppose, let me cook something up, which is probably true. I read it somewhere, but I'll give you the explanation. Suppose I told you that the population of people in India and the population of donkeys in China for many, many decades showed positive correlation. So clearly, you wouldn't suspect that one is causing the other to happen, right? But it would be worth reflecting upon what is going on. Can anyone guess what could be a reason? Hint, history.
When people use their donkey to carry something to China, they leave it there.
Very nice guess, yeah.
War?
Hmm?
War, I mean, there's no war.
There's no war. It's a very good guess.
As the
Good.
civilization improves, you need
Improves in which way?
as civilization improves in the sense there's more people, as population increases, and also so do all the farm animals that you need to do the work.
They start cultivating more farm animals. Actually, the explanation could be a little bit simpler. This has been seen since the 1940s, late 1940s. Both of these countries, they're post-colonial nations. They were more or less under European colonization, but they got out of it at about the same time. Both these countries and throughout Asia, what was the first prerogative of all the governments? To feed the population. Now, there's the Malthus law of population dynamics, right? When you increase resources, when you make food abundant, population naturally explodes. Population will explode of humans, population will explode of donkeys. In all of this, so I could have picked any other country, isn't it? Or I could have taken any two species, right? And also, 1940s onwards is also the explosive growth of scientific breakthroughs. So I would imagine that if I picked up any country anywhere in the world, even Europe, the relationship would be somewhat correlated. Right? So that is looking for latent factors, underlying causes. And then, so this whole correlation causation topic is quite amusing, worth thinking about. Nevertheless, each of us fall into the fallacy. It is something ingrained into our mind. No matter, we may keep repeating this, and we are taught this in school. Correlation is not causation. Yet at the first opportunity, we'll stumble and fall, and we will start saying that. Another similar fallacy, which I mentioned last time, was sequencing. The great Stigler, the great statistician Stigler, and a historian of mathematics, who did many remarkable things. He has written the 7 Pillars of Statistical Wisdom. It's a lovely, beautiful book. I feel that every data scientist should have read that, Stigler's book. And one of the things he mentions is how common it is for people to confuse correlation causation and also sequence and causation. We talked about it the last time, about the fallacy of the people thinking that simply because something came after something, it was caused by it. And by the way, people sometimes do it deliberately. For example, in every country, wherever there's democracy, whenever a new president or prime minister comes, waits. Any good thing happens because of me. Anything that is bad that happens because of the guy, look at the mess he left behind or she left behind, right? So that is again in the same sequence fallacy, right? And the amazing thing is most of us fall for it. Most of us fall for it. So that is it. And I made it rather amusing by saying the most absurd thing, namely, I came to Silicon Valley in the late 1990s, and look, there was a dot-com boom. See what enormous influence I have on technology. Right. So it is as absurd as that. Right. So that is that. Okay. So now coming back to the topic, why did I bring this? This seems to be a far-fetched thing, but now I'll relate it to something, bring it back. See, if I have data, and by the way, this is linear relationship. So what is out of bounds, or what we'll consider for today's topic out of syllabus, is a relationship like this. Suppose I have data like this. What is the correlation here between X and Y? Is there a correlation?
No.
There is no correlation. In one part of the one segment, as X increases, Y increases. Then in another segment, as X increases, Y decreases, right? And then again, another segment, it starts increasing. So this, I brought it out, let me call it the E, to illustrate the converse point. Just because there is no correlation between X and Y does not mean that there is no relationship, right? There is a relationship. For example, this is approximately minus sine X, give or take approximately here. Isn't it, guys? Something like that. So absence of correlation is not an absence of relationship. But a presence of correlation is the presence of relationship, but not causation, just a presence of relationship, a mathematical relationship. There is a function that can put them together, roughly speaking. Are we together? Right. So we are going to look at that problem seriously because it is at the heart of simple linear regression, as well as, and I'll relate it to dimensionality reduction. So I'll unify these topics sort of together. We started with statistics and linear regression, and I'll sort of end it by giving you a unified picture of the whole thing. So now let's go back and look at this. Suppose I have data here. And I have data here. We made data like this. So there is such a thing as a covariance matrix, which is nothing but the standard, the covariance sigma x squared, sigma y squared, sigma xy, sigma xy. This is your covariance. Remember the covariance. But standard deviation is always there for each of the variables. So you create something called a matrix with these values. Basically write it in a square form. This is your matrix, covariance matrix. So forgive me, I would like to introduce this little bit of mathematics, right? And by the way, it should also be a quite intuitive way of thinking in terms of matrices. You realize that in a very compact form, we have given a lot of information about both of these graphs, both of these data points, right? So when you look at A, and let's call this B, would you agree that for A, sigma x squared and sigma y squared will of course be greater than 0, standard deviation. Data is not sitting at the origin. This will be true, isn't it? The standard deviations or variance will be positive. Nevertheless, sigma xy will be 0. So it will be a matrix which will only have values here greater than 0 value here, 0, 0 here. Does that make sense, guys? It will have positive values in the principal diagonal and then this. But when you look at this, this will have greater than 0 because the standard deviation always is greater than 0, right? Variance is always greater than 0. What about this? This is now positive and this is also positive, isn't it? But see, suppose I tell you, and think about it this way, I gradually deform. So now we are going to do a little mathematical game. Let's think through this. Suppose I were to wrap this data, it looks like a circle to you, right? And let's shrink wrap this data. If you shrink wrap this data, what does it look to you like? To me, it looks like an ellipse, isn't it? And I can ask you, can I gradually deform this data here to this circle into this ellipse? So this solid disk, imagine, to the first approximation, into this ellipsoidal disk. And so how would you do that? Now comes a little bit of a magic about matrices. Matrices are nothing but devices that move a point from one place to another. Are we together? If you think about it this way, what are you doing? You're taking a circle and you're gradually pulling it. So imagine that you're working with a pizza dough, which is in a nice round circle, and you're gradually deforming it, a Play-Doh, and you're gradually deforming it into an ellipsoidal dough. When you do that, each point moves to some other point. Not all points move, but most points move. Isn't it, guys? Is that clear? So here is what matrices are all about. Matrices are nothing but operators that move points in a plane. In this particular, in two-dimensional matrices are nothing but things that move points in the plane to other places in the plane. Right? So you can ask yourself, let me give you an example. The way you say that, let me put 1, 2, 3, 4. And suppose you have a location 1, 1. So let's say that this point was 1, 1 is this point, right? 1, 1. Right? X is 1, Y is 1. And you multiplied by this. So the way you multiply, matrix multiplication is you do this funny way of multiplication, and that would be 1 times 1 is 1, plus 2 times 1 is 2, and then 3 plus 1, 3 plus 4. And so that is equal to 3, 7. So what have we done? We have moved it to 2, 3, and 7. 1, 2, 3, 4, 5, 6, 7. And what you have done is you have moved this point to this point with this matrix. Haven't we, guys? So matrices are nothing but operators. It's one reason that you find, especially the physicists, whenever they see a matrix, they say, operator, or transformer. They transform, move points around in the plane, right? Now, so you suspect that this deformation can be given by some matrix, M. Would you agree? Some matrix transforms this disk, which shows no relationship between X and Y, to a pronounced relationship. See, here there is a pronounced relationship. As X increases, Y increases, right? Along this axis, the principal axis. It turns out, so that matrix contains all the information that is there in B, the actual B, right? If you really think about it, the covariance matrix contains all the information, whereas A contained nothing. Can you guess what is the likely matrix that it would be that can transform a disk into this ellipsoid? How about the matrix we just encountered, covariance matrix? This literally does it. Right? This is, by the way, these are little amusing games you play with these things. It gives you a sense of the field. It's no practical value, but you sort of get a good intuition into what all this is. Go ahead.
So the covariance matrix is for the desired shape you want.
Exactly. So what do you think? See, here's the thing. People get lost in algebra, right? There's covariance, oh my God, this matrix. But think geometrically. Geometrically, if I have a disk in which X and Y has no relationship, and I have this nice ellipsoidal shape where there's pronounced relationship, this has information, this hasn't. This information is the covariance matrix. So maybe if I apply the covariance matrix to the points on the disk, it will become this ellipse, isn't it, geometrically? Common sense. Yeah. And that is the intuition. It's very, see, most of machine learning and data science, if you think geometrically, then it becomes practically obvious things. Now comes the interesting thing. You have to take me on faith that, okay, not on faith. So you look at so take me on faith that what I just did for 2 dimensions, is also true for arbitrary many dimensions. Are we together? Now also notice that when you make an ellipse, one axis, one direction of variance is greater than another direction of variance. Data is much more spread out in one direction than in the perpendicular direction. Would you agree? Right. So now let's look at that. And now I'll tell you a beautiful fact. You see these points, I'll color these points. This is the principal axis, and this is the other perpendicular axis, right? Let me call the P1 and P2 axis. Now here is a beautiful fact. All the points in the disk that fell on the principal axis, either of the two principal axes, when they get transformed into the ellipse, you can convince yourself that they only got stretched. Are we together? They only got stretched, right? They did not get rotated. But every other point goes through a bit of stretching and a bit of rotation, right? So now you can ask this question, if that is true and an ellipse is inherently has greater variance along one axis than on the other, pick the axis that has the greatest variance and ask this question, if I took a unit disk of radius 1 and I made it into an ellipse, right? What is the degree of stretch it went through that got stretched? Let's call that lambda 1. Lambda 1. Yeah. Did it stretch along the most variance, the highest variance direction of the data, wherever, in whichever direction the data. So now imagine that this unit disk was data, every point was data, but at this moment, just think geometrically, it got pulled. Lambda 1 is the biggest stretch. Lambda 2 is actually a shrinking, because you notice that nice round circle, now you have sort of squished it, isn't it? If you think of your original circle, it is somewhere, something like that was the original circle, isn't it? So lambda 2, but is probably its value is less than 1. You shrunk it along the second axis, right? But whatever it is the scale. I'll just write it scaling along the second principal axis. Are we together, guys? And now you would also agree that I need a direction. There is a vector. If I look at this, there is a direction, a unit vector along this direction, a direction, this vector, right? And there is another vector. See, guys, is this utter common sense? If you make an ellipse, it has to have a direction associated with the principal axis, and therefore a perpendicular direction to that, E1, E2. And now comes something beautiful, unbelievable. So I won't prove it, but I'll just show you the beauty of mathematics here, of how data and geometry come together, right? This E1 and E2 vectors have a name. Can you guess what it is? Anyone? From your, in one of your past lives, you must have done engineering.
Eigenvector.
These are called
Everyone knows that, but don't know what now.
eigenvectors. And lambda 1, lambda 2 are called
Eigenvalues.
eigenvalues. So this is really the intuition of eigenvectors and eigenvalues, right? If you think in terms of geometry and a disk and see how a disk is deformed by a matrix, which is an operator, you will see that this is what emerges. And now comes something, now you say, but these eigenvectors and eigenvalues, somehow they convey the same information as the covariance matrix, isn't it? The information content of the covariance matrix and this eigenvector and eigenvalues have to match. So how can you bridge the two? So that bridge is a beautiful bridge. So what you do is you take the two vectors. So you remember that E vector will have its own components, right? And then E2 will also have its two components. And so put these two together, create a vector called V, which is E1, E2 together. So it will become a 2 cross 2 vector, 2 cross 2 matrix, isn't it? And now take the diagonal, then create another matrix called lambda 1, lambda 2. This is just a diagonal matrix, right? This is just stretching. If you think about it, you multiply it by 1, 1, all you will get is stretching. Does it make sense, guys? Right. So now here's the beautiful thing. What you thought of as the covariance matrix M is nothing but V D V transpose or V inverse. It is the same as V D V transpose, or the inverse of that matrix. That's all it is. Right? So the beautiful thing is when you take data and you see correlation and you create a covariance matrix out of it, a relationship, that relationship has to have what is algebraically that relationship? No. Has a geometric interpretation. You can shrink wrap it in an ellipse, and the properties of the ellipse are given by this, and therefore this is this, and this is the eigenvalue decomposition of. Now you may say, well, this is a very interesting digression into operators, matrices. What has this to do with dimensionality reduction? Nice detour. I'm reminded of I don't know, can I go in a completely irrelevant digression? Right. So there's a beautiful TV show my kids used to watch called Psych. I don't know, anybody knows about Psych? So we all got hooked as a family to Psych. So there are two characters, Sean and Gus. Sean is the crazy genius. Gus is a very, very bright, sensible fellow. So one fine day, they have to, for whatever reason, it gets into their head that they need to stand for the mayor selection. So they do that, but this is politics. So Gus gives Sean a friendly advice. He says, when people interview you on the press, comes and interviews you, they will ask you questions. Here is an easy way to field it. Don't answer that question if you don't want to answer it. Answer instead a question that you do want to answer, an adjacent question. Then you can confidently go and field as a politician. That's what politicians do. And you can field any kind of press interviews. Right? So as you know, it's a cat and mouse game. Politicians will never answer the question you ask them, and the press will keep pressing on the same question over and over again. Right. So anyway, in this amusing episode, Sean is asked some deep question about poverty in the city and how he's going to handle it. He instead says, brown jelly beans. I like brown jelly beans, or something like that, or blue jelly beans. So somewhat like that, we started with the topic of dimensionality reduction. And I seem to have been talking about brown jelly beans. What has this to do with dimensionality reduction? Isn't it? It turns out that we are staring at dimensionality reduction because think about it this way. If these are the two vectors, then every point here, let me take a point. Every point here, guys, do we see this point here that I put? Let me call this point. This guy, right? Every point has a XY location, but you can also find its location with respect to E1 and E2 along this new axis, new principal axis, right? You can say that this point is some degree of, it has some value A E1 plus B E2, isn't it? Or more formally, we can write it as AB, except that you're in this other vector space done by E1 and E2. Are we together? So now comes the last piece of the puzzle, where we started. If the data looks like this, looks like the situation C, do you realize that if I give the coordinates of a point along E1 and E2, to the first approximation, E2 value may not matter, isn't it? E2 is how lifted you are off E1, principal axis. It may not matter. Like I took the example of the fireside, the campfire, right? That lift may not matter. Azimuthal sort of this degree may not matter at all. So what it means is, and it happens, when does it happen? If you look at situation B, where is it? Intuitively, if you look at situation B, look at this. Clearly, the E2 value, B, the E2 coordinates matter. Too much information would be lost if we ignore that. But in C, would you agree that it doesn't matter? If I were to exaggerate C into a D, let's say, suppose I were to exaggerate it even more into this situation, right? Now, suppose I look at this, would you agree that the second value, the second axis value, it doesn't matter to the first approximation? And so what you can do is when you have this eigenvector V in terms of E1, E2, what you can say, so how will you be able to tell that? See, look at the ratio of λ1, λ2. What happens? As you make it more and more stretched out, λ1 becomes huge, λ2 shrinks. So the ratio λ1 becomes much greater than λ2. Isn't it, guys? And that is when you can say, hey, you know what? Forget the second direction. All I need to know is the value along the first direction. And that is dimensionality reduction. One second. And this dimensionality reduction technique is called principal component analysis. And I have, I believe, reconstructed more or less the original argument of one of the creators.
No, there's a question which I will ask. Magish asked, what is the practical use case?
Oh, we'll come to that. We'll come to that. We will do that actually, right? So guys, are we together here? Right.
One more question. In your example, there were just two principal axes, and there
Right.
were corresponding only two eigenvalues, λ1, λ2, and E1 cap and E2 cap.
Right.
Is it possible that in real use that you may have like n different, you are talking n dimensional space, and therefore you have n different eigenvalues?
Exactly. Yes. So what happens is that it will show you, you will notice that the values precipitously fall. Oh, sorry. The values of your eigenvectors, right? First eigenvector will be huge. Second will be up to here. And third will be, you look for an elbow. Actually, I should have made it more pronounced. Oh, goodness. Let me cheat a little bit and make it like this, right? So second eigenvalue is like this. What happens is, after a little while, right, the eigenvalues become very, very small. They keep on getting smaller and smaller and smaller. So you use your judgment at what point you want to do a cutoff, right? And the whole question is, what is the price you paid? How much information did you lose? For example, in the case of B, you would agree that B, this situation, this case, you did not you lost significant information. In the case of C, B, you lost significant information. C, you lose less information. D, you lose very little information. Isn't it? So there is actually a mathematical measure, which I won't talk about today because we will go into practical things. It is called proportion of variance explained. Proportion of variance explained, PV. And it basically gives you an idea that if I took only the first, let's say 3 axes, 3 dimensions, and threw away the rest of the dimensions, what proportion of the information do I still retain and how much did I lose? You want that value to be high, right?
Say that again.
So see, the proportion of variance explained is, let's say that the first one takes you this far, second one takes you this far, the third one takes you this far. After that, it plateaus. So what you want to do is you want to just pick three dimensions. Because after that, basic common sense principle of diminishing values comes in. The gains are diminished, but your computations will become bigger the higher dimension the more dimensionality that you keep, right? So,
So you pick up the constant value, you try to pick it up at constant value once.
You pick it, you make a graph, and from the graph, you look for the bend in the graph. You say that, where do I reach a point of diminishing returns? Did we get that?
Can I say? Oh yeah.
Yeah.
The way I understand, let's say in the machine learning language.
Microphone.
Oh, you want to say that?
Microphone.
So the practical way I understand, you have n number of dependent variables, right? Now imagine that you can reduce the dependent variables, telemetry collections or information that you needed for predictions. So that's why I kind of understand this. Is it making sense?
Yeah, it's sort of, it is close to that. That's one way of doing it. So now the question comes, this is all fine, but what is the practical use for it? So let's get practical about it, right? First practical use is, if you get data in 10 dimensions, how many of you can visualize in 10 dimensions? It so happens that we live in 3-dimensional space, and the process of evolution and eyes, evolution will only give you what is necessary. Nature never thought it necessary to give you 10-dimensional vision, right? So I'll tell you a bit of a joke from a field that I spent years in, theoretical particle physics. What happened is that first I noticed in grad school, I noticed that people would talk during research years, as you can see and they would use a big number, 26 dimensions. And I would be sitting there thinking, I can't see at all. As you can see in I couldn't see that. And then another graduate student explained, it's this way. See, what you do is, there are some gotchas in high dimension. You know that. You understand that. Higher dimensions are strange, but you know their behavior. But when people say, as you can see in high dimensions, what they're actually doing is seeing in 3 dimensions, but they have the mathematical assurance that in high dimension it behaves exactly like this, right? So they will say, as you can see in high dimension, right? So it took a while for me to get the hang of it, because I used to always wonder, for example, why is the string theory in 26 dimension? I suspected it must have something to do with the fact that English has 26 letters. No, I'm kidding. Right? Well, now they simplified it to 10 plus 1 dimension, but that's that. Maybe a strong case of dimensionality reduction needed there. No, I'm kidding. So, all right, you can't think in high dimensions. So what can you do? You can hope that at least by doing dimensionality reduction to 2 or 3 dimensions, picking 2-3 dimensions, let's say that you picked up a proportion of variance explained is still 60-70%, but at least you can visualize the data, isn't it? Yeah. You have a tremendous benefit in being able to visualize the data in 2 or 3 dimensions. So the visualization helps you develop good intuition, and that is its value. The second value, which is more important, is it isn't just that sometimes less is more. When you throw away factors that matter little, but you realize that this is a peculiar one, you don't just delete some factors, you synthesize new factors. These principal axes are a mixture of your old features, isn't it? They're synthesized from the old features. They actually turn out to be profoundly useful in many, many domains, chemistry, physics, medical. People, when they discover the principal components of data, they sit back and think, what is the intuition? What is the physical meaning behind those principal dimensions scientifically? And quite often they come up with very sensible names and explanations for those principal values, principal components, or principal axes. Are we together, guys? They give it name to those principal axes. And so principal component analysis, believe it or not, has been the workhorse of statistics and data science for decades. In fact, for the longest time, it was the only tool we had, with one or two other things like linear discriminant analysis and so forth, but not many tools did we have access to. You could do lasso regression and throw factors away through regularization, which was like the argument I said, figure out which factors don't matter. But if you want to synthesize them all and find the intrinsic factors that these things give you, this was one of the workhorses for it. Sanjay.
A couple of questions. One is, in the case of father child in the beach under temperature.
Right.
In that case, do you think the temperature would be part of the principal?
Oh, yes. What it would turn out,
yeah.
like, let us say that you're looking at how much ice cream you are selling.
Yeah.
And the input, the factors are of temperature. And let us say there is also some minor things, like, for example, wind speed. Right. So long as the wind speed is moderate. Or let's not take wind speed. Let's say whether it's high tide or low tide or so forth. Now you realize that when you do a principal component analysis, your primary principal axis will have a lot more dependency on temperature. It is called the weightage, the weights, right? It would have, or loadings. People often use the word loadings. It will have far more loading from temperature than from the tide. The phase of the tide,
or even the children in this case,
or the children, right?
So in that case, principal three eigenvector, three things that would come in, maybe the parent, temperature.
No, it's a synthesis of this. It is always mix up though. Yeah. So it takes so it is almost like, you squeeze the lemon, right? Principal component analysis is a way to synthesize from many factors many fewer cooked up factors, synthesized factors.
A combination of the
combination. It's always a combination. And the amount of temperature, the importance of temperature in the first principal component will be higher. It's called the loading. Temperature will have a higher loading on the first principal component, right? So that's how it goes. So there's a whole beautiful field behind all of this. But you have to remember the demerit of principal component is you gain fewer factors, reduction in dimensionality, but what you lose is some direct physical intuition, because now you have synthetic axis, which is a mix of the previous features. And you have to now look at the loadings and put some interpretation and make head and tail out of it. And in just about every field, in many domains, people sit down and give some interpretation to it, right?
So one of the things we discovered, Krishnan, is the loss function description, the diagram.
Yeah.
The best example of principal component dimensionality reduction, right? In a neural network.
Yes. Sort of, yeah. It's synthetic, yes.
So the question, now we understood the linear part of it.
Right.
You showed the sine wave kind of, it's not.
What do you do with that? Okay, I'm coming to that.
That's an important aspect also.
So that was linear. And now the question comes, linear is good, but most data is not linear.
Yeah.
What do we do then? Well, remember the fact that I told you, if data is nonlinear, you can always project it into a different space, which makes it linear. So the opposite of dimensionality reduction is a very powerful thing called kernel methods. There's a whole field called kernel methods and called kernel machines. By the way, support vector machines, after which I named this company, this training place, is a kernel machine. What kernel machines do, or kernel functions do, is you can take, so any data that is nonlinear, like a sine wave, you can lift it to a higher dimensional space where it becomes linear. Are we together? You can find a different space, a different function space, where it does become linear. Once it becomes linear, now you can do a principal component analysis there. So this is weird. You first go to high dimension and then come to low dimension. And so it is sandwiching two sort of opposite techniques together. It's called kernel PCA. right? Or something like that. Yeah. And along with it, there, like people do that. People do all sorts of crazy things. The trouble with this is you have to know which function you use. It's not that easy. But much more common is something called kernel, k nearest neighbor. Like if you want to do decision boundaries, and you go to the kernel space, and from there you apply kernel k. It's called kknn, k nearest neighbor with extra k. So there's a lot of funny things, funky things people do. But there is a better way, actually. There's yet another way that you could do. Suppose you don't need to linearize the data or do principal component at all. Then there are nonlinear techniques. And the nonlinear techniques come from basically graph theory or manifold embedding, right? What it basically says is look at your sine wave, E. If you imagine that you are a little insect, think of it this way. Before you get into bed, your bed sheet is completely flat. Let's say there's a little insect sitting on the bed sheet, sleeping nicely, or walking around, an ant, right? And you get into bed, and what happens after a little while? Your bed sheet is no more straight, it's all curvy, right? But does locally to that little insect, in the any local region where the insect is crawling, the bed sheet still looks flat, isn't it? And so forth. And so the concept is that bedsheet is a manifold. Locally, it looks flat. There's a mathematical concept of manifolds. Now, it turns out that you can argue that in the linear case and in the nonlinear case, data in all situations are close to a manifold, close to a surface or a hypersurface where that data is close to. So data are like the insects crawling on that higher dimensional bedsheet. Are we together? Yeah. That's a manifold way of looking at it. People have applied manifold learning and the whole theory of manifolds very heavily in machine learning. In fact, you could almost argue that it gives you a really geometric interpretation of the whole of machine learning, right? So based on that, you could say that all I need to do is I don't need to straighten the bedsheet at all. I just need to know how to deal with manifolds. Because on a manifold, that insect never realizes that it lives in three-dimensional space. To the insect, it is still living on the bedsheet, two-dimensional space. So that is classic dimensionality reduction. All the data points, all the insects, therefore, can be represented by a lower dimensional embedding manifold. It's an embedded manifold. Are we together? It's an embedded manifold. So that's the theory. And today, I wouldn't go any further in that theory, because time to do some practical, some code. Yeah.
One last question. So what is the question? But I'll ask explain what I mean. So my interpretation is all of this is for better understanding of the data. You're doing all of this.
Not just understanding, it's learning.
Learning
what is essential and what is not.
What is essential? Oh, okay. What are the key variables?
Is machine learning, exactly. Okay. It is highly important. See, I deliberately excluded neural networks and higher end topics. Some of the most powerful techniques, autoencoders, etc., right? They all project data in lower dimensional space. See, all your so-called language models, what they do is when you find that lower dimension where you not only, it's called the bottleneck principle, and well, not related to, okay, think about it this way. When you project data to a lower dimension, machine is forced to focus and understand the essence of the data. I'll give you an example. In this language models, large language models, look at human vocabulary. It's what 3 million, 5 million. These things start with each token, the number of unique tokens will be anywhere from 300,000, right? To these days, these frontier models use 3 to 5 million, right? So each word, each token, therefore, is a one hot encoding in a million dimensional vector. And now think about it this way. A whole sentence goes in, or text encoding. That whole long bit of text with so many words, each word initially starting out in a fairly high dimensional space, or even if you take the initial, so first what you do is you convert the token into a reasonable, each word into a lower dimensional, just word space. It's called the word embedding, token embedding. That token embedding gets position embedding. Many things happen. Let's not focus on that. But at the tail end of that, right? So shush, it goes into that model, and out that comes out before it goes into the softmax is yet another vector. So when you do text, for example, for semantic search, AI search, you get sometimes a vector that's just 1,000 dimensions or 500 dimensions, right? For the case of semantic search, for example. It is the encoder part of the transformer, 300 dimension. And nevertheless, as you will see when you take the large language models bootcamp, quite literally tomorrow morning, you'll see that by converting text into a single vector in low dimension, just 300 dimension, the whole text has been compressed to that, one vector. Nevertheless, it has such a deep understanding of the text that when this discovery was made around 2018, the search engines made a big U-turn. Like they all went heavy on with semantic search. You will see that you show it, you ask it. I'll give you an example. You ask it in a multi-dimension, in a multimodal form, even images, which are high pixel images, right? You convert it down to a 300 dimensional vector, 500 dimensional vector, something, low dimensional vector. And then you ask a question not about house or city or something. You ask it a question about an emotion. You say friendship with animals. That is a relationship, emotion. And sure enough, it digs up pictures from your repository of pictures. It digs up as search results, not just pictures of animals, but of humans loving animals, literally in relationship with animals, right? It brings up quotations from different, we'll do it because obviously you have fed it, you have encoded all those vectors. It will bring up search results from your corpus of documents and images that truly convey a sense of relationship with that that contains friendship with it. So think about the sheer impact of dimensionality reduction. What you did is you took a fancy machine which did nonlinear transform, and at the end of the day, neural networks are machines that do through a whole process of linear, nonlinear, linear, nonlinear, nonlinear, and going to different dimensionality. At the end of it, it is one giant machine that systematically does representation learning and then finally discovers a relatively low dimensional representation of the data in terms of dimensionality reduction, a completely fairly low dimensional representation of a very complex data. Like it could be a movie, I mean, it could be a video, it could be image, it could be a long text, such that with that you can do all sorts of magical things like AI search and generation and whatnot.
So what I'm hearing, dimensionality reduction will still retain a lot of the information, original information.
Yeah, not only that, see, information is one thing. In reducing the dimensionality through a systematic and intelligent process, sometimes you create understanding of the data. That is a unique thing. In fact, there is a principle called the bottleneck principle.
Yeah.
Right? The bottleneck principle says that if an information, you in these neural networks, you deliberately insert a bottleneck, such that the output of that bottleneck is, of course, a low dimensional representation, and then you let it reinflate itself to full. The machine will be forced to understand the data, right? I will make it very intuitive for you. Suppose I tell you, all of you read stories, right? And you must have seen that school teachers will often say, oh goodness, now write this story. Tell us what story you read. And people will write a 5-page story and they will recount most of the facts. That shows memory, that you remember the story. But if the teacher wants to see, did you understand the story? The clever way to do that is to give you and a limit in 300 words or in 500 words, right? Tell the story. Now what are you forced to do? That story was 30 pages long. You're supposed to condense it to a page or half a page. You're forced to understand the essence, the core message of the story, know what is not so essential, and extract everything out of it. So you're coming up with a different understanding of the story, which is not the information, but distillation of the information. You have to distill the information into an understanding. And that is the purpose. That is what, I mean, that is the, for example, you call that the bottleneck principle, right? And so dimensionality reduction has a core purpose. That is what forces understanding in these neural networks of your data. Right? We will encounter it when we do this foundations of AI and this LLMs, etc. You'll see all of these concepts, right? They become very real. This was supposed to be a very lightweight walk through the whole field, but we are going to cover this in the subsequent 4 months in a very systematic manner, right? So guys, let's take a, would it be fair to say we'll take a 10-minute break and then regroup for labs?
Yeah.
Okay, so let's pause the recording, go to the lab. Oh, recording in progress, 1 second here. So I will go into 192.168.1.239. Okay, let's try a lot. All right. We'll look at one of the simplest data sets. This data set is the iris data set. And guys, this is the beauty of it. One day, one fine morning, one botanist decides to go walk over to a garden and look at 3 species of iris and he measures the, if you look at a flower, it has petals and sepals. Biologists will tell you. So for example, in a rose, the petals, if I'm right, they are the rose colored, the pink, the red, and so forth. And the sepals are the green things just below that, right? So the botanist measured for each of the iris species in the garden, the length of the petal, the width of the petal, the length of the sepal, and the width of the sepal. So you end up with 4 features for every data, and then the species of that iris. That's a label, right? So five data points: sepal length, sepal width, petal length, petal width, and what species it is. 5-dimensional data, right? So this is it. You see 5 dimensions in the data. You can load this data. Iris data has only 50 records. It's balanced data, 150 records, 50 records per species. It also harks back to a simpler times when we used to think 50 data points are enough. Right? So, and yet this is one of the classic data points. You cannot be doing machine learning or data science without having at some point encountered the iris data set. So we will take this data set and ask ourselves, what happens if we take the data, the 4 data points, the petal length, petal width, sepal width, and do a principal component analysis of that. So you create a pipeline. First of all, before you do PCA, by the way, this is something important. You must scale the data, z-value it, right? What is z-valuing? Subtract the mean from it and divide the number by its standard deviation, population standard deviation, or sample standard deviation. PyTorch comes with very simple code to do it. So let me walk through the code. As you can see, iris dataset is so common or so much used that it is now baked into the scikit library, a datasets package itself, module itself. You can just say datasets that load iris. You will get that. And you can put it in a data frame. You can look at a few data points. As you can see, these are the values that you get. Now, you notice that some values are much bigger than others. Petal widths are tiny. So it makes sense to normalize it. You can look for correlations between them. Clearly, petal, for example, sepal length and sepal width are slightly negatively correlated. If you know iris, you'll see why. The longer they are, the less wide they are. Then, likewise for petal length and petal width, on the other hand, there is the petals is like size based. So the bigger it is, the more correlated they are. I mean, the length and width are positively correlated. Now, this is basic statistical analysis, pair plots, etc. Make all these pretty plots. But now let's go and do a principal component analysis. It's very straightforward. You create a pipeline with two operations to scale the data using a standard scaler. Standard scaler is z-value the data, right? And PCA, principal component analysis. So as you can see, the entire theory that I taught you boils down to you just using a PCA function and it does it. Right? So, but nevertheless, it is good to know where it all comes from.
Question.
Yeah.
Does the PCA thing do the V, D, and V transport? Is that what it does?
Internally, yeah, it does all of that. It does all that. It does it does the decompositions for you. Right. So now if you look at this, let's look at the proportion of variance explain variance ratio. So guys, look at this graph. If you kept only one principal component, how much of the variance would it explain? Two. With one, you get about 70%, right? You see here, the x-axis here is 70% where my mouse is. Right. With two, actually the values are here, 72, 73%. Right. Now, this is the cumulative value. The second principal component adds another 23% to it, so that the cumulative goes now to about 96%. Right. 96% of the value is explained. If you go to the third component, it adds only 3 or 4%. And by the time you reach, of course, fourth, you add all of it. The residual amount is in the fourth. So would it be reasonable for you to say that if I took only 2 or 3 and visualize the data, I can see most of the information, right? Let's see if that is true. Let's look at the first and the second principal component. That is these are the principal components. This is the transformation. You have transformed the data in terms of its principal components, principal axes. And now you take only 2 axes together and let's go visualize the data. Look at this. Do you think the species are well separated out? Blue, the 3 species of iris?
Blue has completely separated out.
Completely separated out from the
With 2.
Yeah. And you can see that, right? You see how well or how useful it turns out to be. You could actually, and this is an interesting point, you can write a classifier in terms of the original data set. So, you know, if you did a classification, given the 4 properties, petal length, petal width, sepal width, could you predict which species it is? And if you did that, you would realize that your accuracy is fairly high. We can see those values of accuracy. I think I didn't print it out, or did I? The area under ROC curve is very high. It does a pretty good classification. But if actually I should have given the accuracy value. All right. But if I did it with the dimensionality reduced variables, and I took only the first 2 principal components as the predictors, what happens? Let's see what happens. Look at this. Do you think I've lost any accuracy here? Just a tiny bit, isn't it? Area under ROC curve. Just a tiny bit. But what is the advantage of having this dimensionality reduction? I can make head and tail of the data in 2 dimensions, isn't it? Right? It becomes, at least, even if you continue to do your analysis or your predictions in full data, a lower dimensional data helps you gain intuition. It clearly tells you that Setosa species of iris is completely different from the versicolor and the virginica. Right? So that is the value of dimensionality reduction. I'll take, by the way, we have deliberately taken very simple examples so you can follow through this code. Right? Usually you do it with far messier and bigger code. But this is that's why it's so popular for educational purposes. Another one I mentioned to you are nonlinear dimensionality reduction methods. These are 3 species of penguins. I leave it as an exercise for you to do a PCA on it and see how successful it is. But we'll use nonlinear dimensionality reduction called UMAP. See, in this, the data is pretty sort of mixed up, isn't it? They're very close to each other. But, and they're overlapping data in different dimensions. Here it's overlapping. Do you notice that? In this graph, it's overlapping. Right? So you cannot do 2-dimensional plots with the original variables. But what you can do is you can do dimensionality reduction and look at the first and second axis. And notice how far the penguins are separated. The 3 species of penguins are separated. What did you have to do with code? The code is very, very simple. As all code in machine learning, you just have to instantiate the UMAP function, the UMAP object, and it's a dimensionality reducer object. Apply the standard scaler, scale the data, and then apply the dimensionality reducer. By the way, you could have put it into a pipeline, just like we did for PCA, and it gets done. That is it. And now when you look at this, isn't it amazing, right? Now, I'll give you a more realistic value for it, guys. A practical example. I said that languages have vast vocabularies. You do one-hot encoding of tokens in starting with like a million dimension one-hot vector. From there, you go to a word vector, token embedding vector, join position embedding, etc. But finally, when you do text encoders, they produce a vector, let's say 500 dimension or 1000 dimension, whatever, 500 dimension, much lower dimensional vector for the entire text. One of the things you will do when you do the labs here is we will give you text from many subjects, just random pieces of text from different subjects, and you will project them into UMAP. Project them, those vectors, they will become embedding vectors. Those embedding vectors, you'll actually project it down to 2 dimensions using UMAP. And what you will notice is, to your surprise, all of these subjects are well separated out in the embedding space, right? So just think about it. Think about the impact. You've got text, that is, you got, why am I not able to see? Oh, once again, it has, okay, here we go. So you got text for, let's say, 10 different subjects. And you don't tell the machine that these are texts of 10 different subjects, right? You just take a text encoder which creates an encoding of, let's say, 500 or 1000 dimensions. I think we use Matryoshka embedding to bring it down, even down to something like quite literally, sometimes like 60 dimensions, 32 dimensions or something. Then we do UMAP of that to project it, to visualize it. And what we find remarkably is that all the subjects naturally separate out. The text of all the subjects naturally spread out in the vector space, in the text embedding space. And you can see the power of the neural networks, of these transformers, of how well they understand, and they put history completely separate from chemistry, right? And is it any surprise that today they are so powerful as generative models and they answer our questions and so forth? You really see how well they understand these things. You will encounter that in your lab work should you be here. But anyway, that is that. So, all right, guys, I'm going to summarize. It's past 9 o'clock. I'll summarize our course today. First, let me summarize. Dimensionality reduction is yet another pillar of machine learning, a very powerful technique and a pillar with wide applicability. Dimensionality reduction also helps a machine understand the data. It's not just compression, it's understanding of the data, and us also to understand the data. Now, in this short, very fast course, Introduction to Machine Learning, to summarize, we covered quite a few things. We started with basic things, statistics, some statistical concepts. Then we did regression, classification, clustering, and dimensionality reduction. These all look like vastly different areas of machine learning. But let me give you a sort of a unifying principle, a geometric principle. All of these machines, what you do, all the algorithms at the end of the day, they do something called representation learning, so that they learn through various transformations the perfect space to project data in which the problem becomes simple, as simple as cows and ducks and having a decision boundary between them. The last stage of all neural networks, at the end of it, is a linear layer, right? It's a softmax function or linear regression or something. It means that however complex your data is, it has been simplified to a linear problem. In this course, I only taught you linear methods, but you will later on apply and use it for the rest of your, hopefully in the rest of your work. Now, geometrically, you can say that quite often, like for example, regression, classification, they are all search for something, some manifold, embedded, hidden hypersurface. In the case of regression, hypersurface is the hypersurface that the data is proximal to. In the case of classification, the hypersurface is the decision boundary that separates out the classes, the best hypersurface that separates out the classes, right? Or in the language of kernel machines, the best maximal margin hyperplane, but in higher dimensions, a surface, curved surface, that separates out the, in complicated data, it's a complicated surface, but you can project it to higher dimensional to straighten it out. So you're searching for a manifold that separates the data out. In the case of clustering, it's of course even easier. You're looking for subregions, the dense regions within the space where data resides, right? Where it sort of congregates, it's clubbed together, clusters.
It appears that I can do better classification if I use PCA.
Yes, it is sometimes true that regression and classification, if nothing else, you have a better sense of what's going on.
Now, even the decision boundaries are much clearer.
It is clearer to visualize for sure. If you do it in the original space, you don't know, you can't see it.
But will the accuracy also increase?
See, that's a good question. The simple answer would be no, but actually the answer is mixed. Sometimes yes, sometimes no. Because see, to the extent that some information is lost, one could argue that you'll never get as good a decision boundary as in the original thing. But what in reality happens is, sometimes it is not the information, but the noise getting lost. And so you actually have a gain in performance. So those two have been observed. Yeah. Go ahead.
So when we try to always try to make it linear,
yeah,
we should be losing something.
No, you don't.
You never lose.
The whole point of neural networks in this thing is, well, when you come to it, you'll see. It's representation learning. The point is that every data, in it, there is some space in which it is truly linear. So you're not losing anything by going to that space. Okay, I'll give you an example. Should I make it very concrete immediately? I said, see, all of these arguments become obvious when you think geometrically. So let me give you a geometric argument. See, suppose the data is in a circle. I'll give you an example, right? Data is in a circle. all points inside the circle are, let's say, green in color. All points outside the circle, let me see if I can make it bigger. All points outside the circle, let's make them red. Pretty obvious, right? Positive, negative points. Think of it. Now you say, look at the decision boundary. What is the decision boundary? It's a circle. It to you looks like a curved. It's certainly not linear decision boundary, right? A circle is the very definition of not linear, almost. Now, not a line. Now, this was your x-axis, y-axis, right? Now, do one thing. Create another axis whose coordinates are x squared. Now, I can choose to do that, y squared. Literally a new coordinate system where the axes are x squared and y squared. So x prime is x squared, y prime is equal to y squared. So for all you do is you have data as xy, add two more columns, x squared, y squared, and ignore the first and just look at the relationship in this new coordinate system, right? What you will notice is surprisingly, convince yourself, right? And has this data transformed to this? And what happened to your decision boundary? It's straight. And therefore, my claim that for every curved, there is another space. In this case, I didn't even have to go to a higher dimension, right? In another two-dimensional space, the problem linearizes. Now, you can say, well, circles are special. I could have made it into let's say that ellipse. Let's go complicate it slowly. I could have made it into an ellipse. Then you just need 4 degrees. You need 4 axes, x, y, x squared, y squared. Why? You know why? Because every ellipse can be represented as a x squared plus b y squared plus c x y plus dx plus e y plus, I don't know, f is equal to, I'm just writing an algebraic equation. I think some of the terms are missing in an ellipse, but let's pretend that they're there, right? So now, suppose I have a 5-dimensional space. Then all the points inside it are, let me call this a function, f, g, let me not use the word f, e, f, g, e, g, right? fxy is equal to this. Now, convince yourself that fxy less than 0 are points inside the ellipse, more than that are points outside the ellipse. So all I need to do is now represent the data in this space, right? So you can do that. See, it's a whole theory. Like this is the whole theory of kernel machines and so on and so forth. But you should take it as a fact that every curve, there is another dimension, another space in which the curve flattens out. And you don't lose any information in going to that. Are we together? You don't lose anything. And it gets more complicated. Now you say, what about sine wave, sine x? So sine x, let's take because you brought sine x. The sine x expands out to x minus x cubed over 3 factorial. Well, you just need to project data in an infinite dimensional space where all of these are the terms. Now there's an even better practical way. You just create a variable x prime is the sine of x and you're done. Right? Then if y is the sine of x, then if you project your data and you write y and x prime, oh, it's a straight line relationship because x prime is the sine of x or something like that. You can play these games, right? So see, it is now you say that, well, this is cheating. This is too trivial. What I'm trying to do is get you into the mindset that this really is true, right? there are transformations of the input variables that will put you in a different space where data does become linear.
In our curious, in one of the classes,
Mhm.
want to look at how the information gets embedded into the vector, the word sentence.
That's right.
especially when-
Yeah.
So that's
Oh,
where
yes.
the real value appreciation will come.
That's right. In fact, we are going to do it in the first 2 weeks itself. Yeah.
Question.
Yeah.
The question that was asked about compression, right?
Mhm.
Now, if you retain the eigenvector or PCA, the matrix, you can do the inversion of the.
No, you lose some.
You lose.
The whole point is
Ah.
that if you use PCA or any one of these, and you throw away some of the dimensions, you're losing some information.
How much?
It depends upon, it's again the proportion of variance explained.
Variance.
Yeah, things like that. In the case of PCA, yeah, how much you'll be able to invert back.
Thank you.
All right, guys. So thank you for being part of this journey. I hope you enjoyed it and hope it was helpful.